Okay guys, welcome back again. This is Uncle Sam online tutorial. This is day 6 of going live on TikTok. One moment guys. One moment. Alright guys, good morning, good afternoon, good evening from wherever you are joining from. This is Uncle Sam and we are here once again to learn and to transform beyond knowledge to gain understanding. This is Uncle Sam and this is my day 6 of going live on YouTube. Yes, trying to, and my job here is just simple, trying to make being smart the new cool in town by exploring concepts related to math, and not just exploring it, breaking it down in such a way that it will be very very easy to assimilate, because that's one thing that I love breaking down concepts into assimilatable pattern in a way that is very very easy for you to look at it and say, aha, this is what this is supposed to be. So we are here again to talk about what is on the board, which is an introduction to logarithm. Since last week, Monday, we've been talking about the concept of indices and what the concept of indices is talking about, how that indices, the basic idea of indices is trying to express numbers in a certain way. And what is that way? In terms of having a base and a power. Because indices has to do with concept of index, and index in maths talks about power. And I also mentioned that in order to talk about power, there must be a base. That's the basic ideology in mathematics. So we explored the different aspects of indices and we wrapped it up on Tuesday. On Wednesday this week. Now we're going into introduction to logarithm. But before we go into introduction to logarithm, we're going to solve one question on the last topic we treated on indices, which is equations, indices involving equation, and by extension, look at the equation that is involving quadratic equation. So I'm going to bring one question in, we solve that, and then we'll get into what we have for today, just to refresh our mind. So look at the equation that we're going to be solving now. So we have an indicial equation, which is 3 raised to the power of 2y minus 10 multiplied to 3 raised to the power of y equal to -9. Now this is an equation that we're going to be considering, and we're going to consider it together. Please pay attention and follow me on this journey. Let's do this together. So if you look at this expression, we are asked to find the value of y. So how do we go about solving this equation? Now, one thing you need to know about indices, this is already arranged. I don't think there's any simpler way we can express this. But one of the things that you need to know in indices is, it's not just about knowing how to compress number. It's not just about knowing that if I have 3 raised to the power of 2 multiplied to 3 raised to the power of 3, it's going to give me 3 raised to the power of 2 plus 3, and that will give me 3 raised to the power of 5. Sorry. It's not just enough to know this. You also know that you can actually reverse engineer this to get this original function. What am I trying to say here? Simply put, what I'm simply saying here is, if I have 3 raised to the power of 2y here, and I'm having a subtraction sign, which is not a division sign. If it was a division sign, I would have said, oh, let's employ one of the basic rule of indices, which is the division rule. But here we're having subtraction. So simply demarcating that this is a section on its own, and this is another section on its own. So what do we do in this particular case? It's quite simple. We're going to reverse engineer this 3 raised to the power of 2y. How do we reverse engineer that? We're going to do this, represent this as 3 raised to the power of y, and then everything here squared. Now, why did I do this? There's a reason why I did this, because I want to represent 3 raised to the power of y as a separate entity on its own. Now, these and these are still the same thing, because if you have a bracket separating the expression, what we can simply do is actually to multiply the expressions together. And if we multiply it together, you're still going to get 3 raised to the power of 2y. So we have not done anything much here, we just separated this. One moment, guys. One moment. I'm having a bang on my door. One moment. No, you are disturbing me. I'm busy now. Later. No, Oh God, you're disturbing me. Don't make any noise here. I'm doing it right now. So sorry guys. I'm so sorry. I had a form of distraction. I apologize for that. Thank you, Avanish. Thank you so much. Kylo, welcome, Kylo. My educational qualification. Well, I hold a Bachelor of Engineering. I'm a graduate. I studied electronic and computer engineering. So yeah, thank you for asking. Thank you so much. So I'm very, very sorry about the earlier noise. We're going to continue with what I was trying to say. So what I was trying to say in essence is this, that we can represent 3 raised to the power of 2y. We can rearrange it in this way. And this is just reverse engineering it so that we'll have the one of the basic laws of indices, which is the bracket power law. When you have an innermost power and an outermost power, they end up going to multiply because you can expand these to give you 3 raised to the power of y multiplied to 2. And that will still give you back 3 raised to the power of your 2y, which you have originally here. But because we know we're trying to express this in terms of a quadratic expression, that is why we'll have to go through this route to reverse it. And you're going to see what I'm going to do with this. So I've reverse engineered this to give me this. I've done that. And then put my negative sign, 10 multiplied 3 raised to the power of y equal to negative 9. So what can I do at this point? Now this is where it gets interesting. And I'll say let 3 raised to the power of y be equals to x. So anywhere I say 3 raised to the power of y, I'll replace it with x. And by doing that, this becomes x. Then there is a square. You now see the why I had to reverse engineer it. I had to reverse engineer it from what it is here to this, so that I'll be able to represent it in terms of a quadratic equation. That is the sole purpose. So once I've done that, this square will now come and attach to the x here. That is it. And then we'll go forward and this becomes minus 10 multiplied to 3 raised to the power of y is still here. I'm going to replace it with what? X equals to negative 9. So this is what we'll have at this point. And then we can simplify this because 10 multiply x will give us 10x. So that this gives us x raised to the power of 2 minus 10x equals to negative 9. And then I can do one more thing to make it a complete quadratic equation. I can decide to push this negative 9 that is on the right hand side, push it to be on the left hand side. And if I do that, the negative sign, because it's crossing the equality sign, is going to change and become positive. So this becomes x squared minus 10x plus 9. Now I cannot leave this right hand side empty, so I must attach a value there. And what other value to attach than what? 0, because it doesn't change anything. And voila, this is our what? Quadratic equation derived from what? This indices expression. We're putting a quadratic equation. So we'll now express this. Now we'll go on to solve this. The quadratic method. And from the last class that we had on Wednesday by 4 p.m. West African time, I mentioned that there are a couple of ways you can solve quadratic equation. There is the factorization method, which is what we're going to be applying here. And then there is the completing the square method, and there is the quadratic formula method. For the last class, I used both factorization, and based on requests from one of our viewers, the viewer mentioned that I should use quadratic formula also. And I used quadratic formula to solve the same question that we're examining. You can look up the last live session that I have. You see the video where I did the live session, and then you follow up from there. So now I'm going to be examining this x squared minus 10x plus 9 equal to 0. So I'm going to solving using factorization method. That's what I'm going to use to solve this given problem. So how do I go about solving this? Well, let me write it out here so that it will be visible. X raised to the power of 2 minus 10x plus 9 equal to 0. So what factorization method simply means is, first, you take this value, multiply this last value. Take the first expression, multiply to the last expression here. It's more like saying x squared multiplied to 9. It's going to give us 9x squared. We're trying to factorize here. And then once you have done this, you simply find two values that once you multiply those two values together, they must have an x each. If you multiply them together, you're going to be what? Getting what? 9x squared. And if you try to add or subtract them from each other, you're going to be getting what? Negative 10x. Let me repeat it. We first of all multiplied x squared to 9. And mind you, if there was 2x squared here, you're going to have to multiply the 2x squared to 9, and that will give us 18. Just so you know, everything here is what is multiplying. I'm trying to give an expanded view of what is going on when we're doing factorization method. So for this case, in the coefficient here is 1. We didn't really consider it. So we just multiply x squared to 9, positive 9. And that gives us positive 9x squared. And then the next step is this 9x squared, split it into two values. So that those two values, when those two values multiply themselves, of course each of them must be bearing the variable x. If they multiply themselves, it will give you 9x squared. If they are added or subtracted from each other, they're supposed to give you what? Negative 10x. And if I do that, the two values that comes to mind is negative x and negative 9x and negative x. Why? Because if I do negative 9x multiplied to negative x, negative multiply negative is already positive, and then 9x multiply x gives me back what? 9x squared. So we have satisfied the first criteria. The second criteria is if I subtract or add them together. If I do negative 9x plus negative x, if I add them to each other, it's going to give me what? Negative 10x. So I've gotten the two values that I'm looking for. So the next thing that I'm going to do here is to replace this negative 10x with these two expressions. So it's now going to be x squared minus 9x minus x plus 9 equal to 0. So I've not really done much. Since I've gotten those two factors, we replace that two factors with what? We replace it to this 10x. Because if you join them back together, negative 9x, negative x is still going to give you negative 10x. And at this point, what you simply do is you factor two parts of the expression. If you factor here, you factor here. So what do we do now? Once we have factored in the two parts, make them to be a pair. We now look for what is common. If you look here, you have x, also have x here. So it simply means that x is common. So I'll bring out x, bring it out of the bracket, open a bracket, and then the next thing I'm going to do is use this x that is common, divide each of the expression. If x divides x squared, you're going to be left with just x. So that if you multiply it back, x times x, you get your x squared. So we're not really done much here. Minus, if x goes on to divide 9x, it's going to give us just 9. So this is what we have. Now, we do the same factorization for x plus 9. Now, what do you think is common between x and 9? Visibly looking at it, there is nothing common. But there is a default value that we can actually bring in anytime we don't have something common in a given expression, what we want to factorize, and we really want to factorize. What we simply do is what? We bring out 1. We introduce 1. Yes, because 1 is a factor of any given number. Every variable, 1 is a factor because 1 can divide virtually everything. So once that is done, we just use 1, divide x. The same thing as saying x divided by 1. The same thing as x plus, the same thing happens to 9, equal to 0. Now that we have done that, now I made a mistake here. This is supposed to be negative. Why is it supposed to be negative? It's supposed to be negative because you know that because there is a negative here, this negative 1 is what is going to expand back this bracket. So if I left it as positive, I'm just using this to tell you the importance of sign in quadratic expression. If I left this to be positive, let us now go back and expand it. If I use negative 1 to multiply x, it's going to give me negative x, which I have originally. Good and fine. And if I use negative 1 to now multiply negative 9, is it going to give me positive 9? No, it's going to give me negative 9. And that is why you need to switch up the sign here to be negative. So that if you have to expand back, negative 1 multiply x, negative x. Negative 1 multiply to negative 9, positive 9. That is it. And so, another way you could look at it is whatever value you get for this bracket here should tally what you have for the second. That's how you do it. So once we've gotten to this point now, what you simply do is you tell us, pick this factor here, this value that you factored out, x, then pick this one, put it inside the bracket, minus 1, put a bracket, and pick any of these, x minus 9 equal to 0. So this is what we have. Yes, George, brilliant, thank you. Thank you, George, thank you, Watson. Thank you. Thank you, let's finish it up. Thank you, guys, thank you so much. So this is what we have at this point. So if this is what we have, it simply means that x minus 1 and x minus 9, x minus 9 equal to 0. And if it's equal to 0, this is what it simply means. Because these two things are together, it simply means that they are multiplying themselves. Remember, my goal here is not just to come and do the calculation. I love the explanation, the conceptual idea behind what we're doing here. And that is why I'm taking time to, convert this to a story, telling you a story of what is going on. Because to me, it's like a story, telling the story, and not just about solving it. And I love exploring it or looking at it that way. So at this point now, you know that when two things are together, they are multiplying themselves. So simply put, what this is trying to tell us is that x minus 1 multiplied to this is equals to 0. And that can only be true if x minus 1 equals to 0 or x minus 9 equals to 0. Now you know the reason why once we get to this point, we get to split it. Because if two things are multiplying themselves and the result is equals to 0, it simply means that either of them must be equal to 0. So either the whole of here is equals to 0 or the whole of this one is equals to 0. And if that is the case, we can now go on to simplify. Now at this point, we want to make x on both sides to now become subject of the formula. So what do? For this side, we add 1 to both sides. Both sides. And then for this side, we add what? 9. That is positive 9 to both sides. Another way you could have done it is to move negative 1 over to this right hand side. And by doing that, the sign changes. So this is also plus 1. The same way, I'll come here and say x minus 9 plus 9 equals to 0 plus 9. So that negative 1 cancels positive 1. And then 0 plus 1 is equals to what? 1. So that my x is equals to 1. Or negative 9 cancels negative 9. And I'm left with x equals to 0 plus 9 will give me what? 9. So it implies that my x is equals to 1 or what? 9. But we're not done. Remember that we're asked to find the value of y, not x. We are the one that introduced this value of x. So we'll go on and tell ourselves, bringing back the original concept, that both x is actually equals to 3 raised to the power of y. That's the original value that we got, that we had originally, that we switched to become x. And if that is so, we're going to replace our x to become what? 3 raised to the power of y. So it simply means that 3 raised to the power of y is equals to 1, or that 3 raised to the power of y is equals to 9. And what can we do here? Well, we are looking for y. Why? Is there something we can do to this one? I know that anything raised to the power of 0 is equals to 1. So even if I want, I can do 200 raised to the power of 0. It's still going to give me 1. But in this context, I don't want to go really, really far. This is the base I should be targeting. So I can replace this one to be 3 raised to the power of y is equals to 3 raised to the power of 0. Why? Because there's a law in this where if the bases are the same, it simply means that their powers must be the same. So it implies that our y is equals to 0 for this part. Then we'll come here, we'll do the same thing. 3 raised to the power of y is equals to, I can also represent 9 to be 3 squared, that is 3 raised to the power of 2. This is same thing as 3 raised to the power of 2. And applying the same thing I did here, which is, if the bases are the same, simply means that their powers must be the same. So it simply means that my y is equals to 2. So this implies overall for this given expression that for this to be satisfied, my y must be equals to 0 or what? 2. Brilliant. So if I go to the chart, Watson, thank you so much, Watson. You got the answer. Brilliant. Wonderful, wonderful. Thank you so much. So this is what we examined in the previous class when we discussed about indices involving equation, and by extension, we talked about quadratic equation. I hope this makes sense to you. Now let's get into what we have for today, which is introduction to logarithm. So take a screenshot. I'm going to clean this in 5, 4, 3, 2, and 1. So clean these up. Clean these up. And then we'll talk about the concept of logarithm. Now, one thing you must know about logarithm, 1 minute. Now, one thing you must know about logarithm is quite similar to indices. Why? Because the whole idea of indices is representing or expressing numbers expressing numbers in a certain way. In the same way, logarithm is doing the same thing. We are expressing a certain number in a particular way. So I have some definitions here that I want to write out on the board so that it will be easy to sort out why x is equals to 3 raised to the power of y. Okay, like the before now, oh, I'm so sorry, I didn't see your question earlier on. Before now, the original expression was 3 raised to the power of 2y minus 10 multiplied 3 raised to the power of y is equals to negative y. And we did some adjustments here, and we represented this to be 3 raised to the power of y, then everything raised to the power of negative, anything raised to the power of 2. So we kind of reverse the process where we now split this, and the y comes inside the bracket and then the 2 outside, so that if you expand it according to the bracket power law, if I go on to multiply these two together, I'm still going to have 2y as the power as I had here. But the reason why you had to go through this route, and then multiply to 10 times 3 raised to the power of y equals to negative y. At this point now, this is what we now did the swapping. We said let 3 raised to the power of y be equals to x. That's what we did. And then we replace this to be x, attach the square now, minus 10 multiply to replace this with x equals to negative 9. And that's what we did. So that this becomes x squared minus 10x equals to negative 9. And then you move this over to the left hand side, it now becomes x squared minus 10x plus 9, because negative comes over the here, it becomes positive. So this is what we did. And that is why when we now found our value of x to be 0 or 9, we now have to reverse the process, because we're not asked to find x, we're the one that introduce x into the given expression. Okay, thank you. I'm glad that you understand, aspirant. Brilliant, thank you. Thank you. So I just had to make sure that you guys are still with me. Diano, thank you so much. Thank you for being here. Really appreciate. So like I said, I want to talk about the basic introduction to logarithm, and I want to give a very short note based on the research that I made and things that will help you to understand, because the way I like doing it is this way. I like doing it this way. I like having a conceptual idea, because every topic you see in mathematics is first an idea. It was first an idea, it came as an idea before it was now compressed based on research, and then it was compiled to become a topic. So that is more like learning from first principle. Having what the particular concept is talking about visually or conceptually, so that no matter the extent you go on that particular topic, the idea, the basic idea is still there. So that is why I'm going on with this. So just some basic things to write out. Logarithm, like indices, is a technique of expressing numbers. Yes. So that's why I say that they are similar, because indices is just a way of expressing number. Just like in indices, you have that I can express 9 to be 3 raised to the power of 2. That means I can express 9, which is an ordinary number that we are all used to, into having a base and then raised to the power of something. Yes, which is something as 3 multiplied to 3. So that's the basic idea of what indices talks about. And just like this, indices is a technique, logarithm itself is also a technique. So just like indices, logarithm, like indices, is a technique of expressing numbers. Then technically, it's just a short note. Technically, this is the definition of logarithm. The logarithm I'm so sorry guys, I lost connection there. Very, very sorry about that. So, but we are back. So we have logarithm, introduction logarithm. And I said this is just a short note to summarize the whole idea of logarithm. So sorry, I'm going to work on my internet. Logarithm, like indices, I've already mentioned that is a technique of expressing numbers. And I now said, technically, based on research, I want you to have a conceptual view of what logarithm is talking about. And that is why I have to give like a brief theoretical explanation to it before we get into mathematical aspect. Trust me, if you go through this route of learning, which is having a picture, because human beings were designed to work with pictures. That's why I can remember memories of activities that you've done over a long, like in a long while. You can still remember it just by somebody reminding you about it. The whole memory just flashes like a flashback because we are visual beings. And if you start exploring or looking at math that way or anything you're learning visually, having a conceptual view, it will be so much easier for you to assimilate. So let's go. So technically speaking, the logarithm of a number to a given base, that means the log of a number to a given base, is the value of the power. It's equal to, it's more like saying it's equal to the power to which the base must be raised in order to produce that number. So this is the expression, this is how it is what represented. So simply put, the logarithm of a number b is the number, a is the base, and c is the power to which the base a must be raised to give b. So you see the interconnection. So just like normal indices is like a technique of expressing numbers, logarithm itself is also a technique of what? Expressing number. So once we have a particular number and we know the base, what we're looking for in indices is how many times or what power would the base be raised to in order to give us the equivalent of that particular word value. So in essence, technically the logarithm of a number to a given base is the value of the power to which the base must be raised in order to produce the number. So this is what I put out here. Log b base a equals to c. This is what it simply means. So this is said that we can represent this to be that a raised to the power of c equal to b. This is the basic idea of what logarithm is talking about. The base raised to the power of what? C, what you have here, will give you the value of the log, which is what? Your b here. That's the basic idea. I hope this is clear. So the next thing we're going to be examining now we'll have like a conceptual view, something to hold on to. All throughout logarithm, this is what we are talking about. Base and power. Base, log of a number to a particular base. That's what we're discussing. So this is the basic conceptual idea that I want you to hold on to. Maybe after now you can still do a bit of research to tie everything down by yourself. But this is the summary that I just brought to you. So the next one I'm going to be looking at is the laws that govern logarithm. So I'm going to clean this in 5, 4, 3, 2, and 1. Thank you, aspirant. Thank you so much. Thank you. So I'm going to clean these up. And then we'll examine the different laws governing logarithm. So laws of logarithm. I'm going to be breaking these laws down so that it will be very, very easy for assimilation. So let's get on to this. Once we finish the law, I think we'll just do maybe a simple example and then we'll call it a day. And then I'll be live again on Monday next week. Monday, please take note. I go live on Mondays, Wednesdays, and Fridays by 4 p.m. Watt, that is West African time. That is when I usually go live and continue from there. So let me be sure that I finish up these laws. It's going to be interesting. The first law is the addition stroke product law. Now, what is the addition stroke product law? The reason why I mentioned at the start of this class that indices is quite related to logarithm is because basically they make use of the same operators, because for indices, multiplication is same thing as taking one of the base and summing up the power. So multiplication And multiplication and addition also play a role in logarithm. So if we get on to it now, it's something of this sort. If you have log b base m, okay, let me reverse it. Log m base b added to log n base b. It is equal to, take one of the log, take one of the base, which is b, and then multiply, open a bracket, multiply their logs, m n. This simply means m times n. Yes. So provided that they are in the same base, we can actually what? Pick one of the base and then multiply the log. So for example, if I have log 3 base, let's say base 9 plus log 3 base, let's say 2. Yes, I can go on to, since the bases are the same thing as saying pick one of the base 3, and then multiply 9 times 2, and that will give us what? Log 9 times 2 is going to give us 18 base 3. This is basically what the addition stroke product law is talking about. Can I show the proof of the logarithmic law? Yeah, that's what I'm saying here. That's the proof. This is the exact proof for this addition to product law. That is the proof. Yeah. I hope this makes sense to you. So this is basically it. Provided that they have the same base, you just multiply the logs. That is what it simply means. And then we'll go on to the second law. Since you guess, you can help me by guessing. Since addition talks about product, then subtraction, somebody help me in the chat. Subtraction should talk about what? What should it talk about? Somebody in the chat. Can somebody help me in the chat? I'll just wait for like a minute. Can somebody help me in the chat? Since addition talks about product, subtraction should talk about what? Any idea? Any idea? Any idea in the chat? What up, chat? What up, chat? Any idea? Okay. Division. Yes. Division. But let me put it. Thank you so much. Thank you so much. Why? Thank you for that input. But when you talk about subtraction, it's actually what is known as your quotient. Quotient law. Because if you look at this now, let me use this opportunity to clear something. When you're talking about product is not multiplication. Yes, I used to fall a victim to that. I used to think that product is multiplication. No, product is not multiplication. If I have A times B and is equals to AB, this is A multiplied to B. The product of A multiplied to B is what? AB. That is the answer that you get after you have multiplied certain values together. That is what is known as your product. Same thing with your quotient. Quotient is not division. Quotient is not division. If I have 4 divided by 2 is equals to 2. This is not quotient. This is quotient. So what is quotient? Quotient is the result you get after you perform a division operation. That is what quotient is all about. So thank you. Driving Scope, welcome fam. Welcome. So I hope you have that in mind. So this is the same thing I'm going to be doing here. So I'll use the same expression. I'll just change the sign to the subtraction. So it becomes, if I have log m base b minus log n base b, see, they're still having the same base, is equals to pick one of the base and then divide their logs, which is what? The first becomes your numerator, m, and the second becomes your what? Your denominator. This is what it simply means. This is what indices tell, what logarithm tells us. So as an example, let's say as an example, we can do something of this sort. As an example, we can do, if I have log 3 base 18, then minus log 3 base 2. What's it going to be? Well, according to this law that we have here, since subtraction simply means you have to divide them, you have to find their quotient. Since the bases are the same, pick one of the base. And then you divide their log, which is 18 divided by 2. And that's going to give us what? Log 9 base 3. This is the proof of the second law of logarithm. So you just what? Divide them. I hope this is making sense. So let's go on to the third law. Third law. Let's go. No time. Answer will be 2. Yes, brilliant. If we have to reduce it further, which I'm going to come to. Yes, I want to start small and then push it up. For now, I'm just leaving this as log 9 base 3. But we're going to get to the law that talks about how to further compress it. Thank you, Thriving. Brilliant. Thank you so much. So the third one is now the power law. This is what we're going to be using this to, this end product for this subtraction part. We're going to be using it to examine the power law. So power law. So what does power law state? If I have log m raised to the power of n and then having a base of b, it is the same thing as take what? The power, which is what? The n here, multiply it to what? The log m base what? b. So I've not really done much here. What I simply did, if your log is having a power or can be reduced to a base and a power, because it's not going to come this way. It's not going to come, most of the time, the question doesn't come with the log already having a power. It comes in such a way that you can actually reduce the log to be raised to the power, a base raised to the power of something. So you can actually do that. So what happens is you have to take the power and what? Multiply what? To the log of m to the base of what? b. So as an example, let us use this to solve this. So it's something like saying log 9 base 3. How do we apply this law here? Well, like I said, it does not really come well set most of the time. Sometimes you need to do some deducement and do some simplification in order to make this to look like this. So if I look at 9, I know that 9 is something as what? 3 squared. So that means I can reduce this 9 to become 3 squared. So it becomes log 3 squared base 3. Yes, you see I've reduced this. So sometimes you need to do that by yourself. And once you've done that, you now apply this power law, which is take the power and then multiply what? To the base. So this becomes what? 2, which is the power multiplied to what? Log 3 base 3. So this is what it simply means. And then this will now lead us to the next law, which is if you have a log that has the same value as the base, is equal to 1. So this is same thing as this log 3 base 3 is same thing as what? Being equal to 1. So this can be 2 times everything here 1, which is equal to 2. But we're going to look at that law in the next phase. Can you mathematically prove the law? Mathematically prove the law. Well, the mathematically proving that I know of is using a value to see that the law actually works. But if you're talking about the derivation of the law, no, I can't really do that. And I'm not really seeing a place where it is done. So it's more like substituting values to verify. So what we simply do is verify the laws. We verify the laws that they actually work. So thank you. So I'm going to clean here. If you want to take a screenshot, please take a screenshot real quick. I'm going to clean this in 5, 4, 3, 2, and 1. Aspirant, it's a full understood log for the first time. Really? I'm so happy. Aspirant, I'm so happy. Thank you so much. I'm very happy. Appreciate your teaching. I genuinely love your. Thank you, Driving Scope. Thank you so much. I'm so happy. Thank you. That really gladdens my heart. Thank you. So the remaining thing I need to do is to finish up on the log before we call it a day, and then we'll come back next week Monday by 4 p.m. West African time. So I'll clean this now and go to the fourth law. The fourth law, which is, we'll call it the logarithm of same base. Logarithm of same base. Logarithm of same base. And that's exactly what I simply said here. So if I have an expression log b base b, log b base b, that means I have the same log to the same base. it's just equal to 1. Yes, that is it. Anytime you see a log to its base, is same thing as what? 1. And remember the original expression that I gave you about logarithm, where that if we have log b base a equals to c, is same thing as that my b is equals to the base raised to the power of what? C. So you can still apply that here. So if I apply that here to prove the law, we can simply say, oh, since log b base b is equals to 1, it simply means that since this is the base and this is the power, it simply means that the log, which is this b here, is same thing as the base, which is b raised to the power of 1. And is that mathematically true? Yes, because anything raised to the power of 1 will still give you back that same thing. So simply means that b is equals to your b. So this law is proving to be true. So it's actually what? True. I hope this makes sense. So anything that has the same what? The same value of the log and the base is equals to 1. So example, what we have here, this log 3 base 3. That's why I now told you that it's equals to 1. Yes, because this 3, if I switch up and say that 3, which is the log, is equals to the base raised to the power of what? 1. So it's still the same thing as saying that 3 is equals to what? 3. So these are just extras to further simplify what we are saying. We have about 2 more laws or so to wrap up for today. So this is like a special law. The 5th one is a special or derived law. This one is very interesting, trust me, very, very interesting. So what does this special law talk about? Well, the special law tells us that if I have log 1 and then base b, that it is equal to 0. Well, it's not just about the law, because someone asks, why ask something about proving the law? Well, we're going to prove this one. Yes, we prove this, we're going to also prove this. How is it that log 1 base b is equals to 0? And your b is the base, and that base can be any base, can be base 2, base 4, base 10, base anything. So anytime we have log 1 having the base of anything is equals to 0. But how is that true? Well, we say how to employ the basic rule of what? Logarithm, which is if I have log b base a equals to c, then my b is same thing as the base, which is a raised to the power of what? C. So if we go on to apply that here now, what are we going to do? We see that it's just saying that 1, which is the log, is same thing as what? The base, which is b raised to the power of 0. And remember, in math, anything raised to the power of 0 equals to 1. So this is the same thing as saying that 1 is equals to what? 1. So this law is already proven. I hope this is making sense. This is the proof for this particular law. And then the sixth law, which is called, I wrote it down here, change of base law. This one is quite interesting. So let me give you the way that it looks like. So if I have log m base n, if I like log m base n, indices affords us the opportunity to actually change the base of a given expression. So this can be represented as log m base x all over what? Log n base x. So what did we do here? This n was serving as the base before, but indices gives us that luxury that when a particular expression in logarithm is not really working out the way we want it to work out, we have the liberty of changing their base. And by changing the base, each of them will not have the same base. So let's say you're having a number here, and you see that there's no way you can reduce them. You can now add a new base to them, where the log now becomes the numerator, and then you have divided by the base becomes what? The denominator. All now having a new base. So I'm going to use an example to further explain that. When I clean up here, I'm going to clean in 5, 4, 3, 2, and 1. So your duty is now to think of the base that you apply to be able to give you what you want. So as an example, if I have log 125 base 5, log 125 base 5. Although I can actually simplify this, but I can decide to do something quite interesting. I can decide to say that this is the same thing as, or let me start by saying putting both in what? Base 10. I want to put each of these expressions in base 10. And remember, once I attach a new base, this value here will now become the numerator, then this over the base here becomes the denominator. So it becomes log, putting the new base, which is what? Base 10, and then have your 125, divided by what? Log, still the same thing as base 10, and then you have your what? 5. And then from here, I can go on and simplify. What can I do here? Well, I know that 125 is same thing as what? 5 raised to the power of 3. 5 times 5 times 5. That will give me what? 125. So I can actually what? Simplify this to become log 5 raised to the power of 3 base 10 all over log 5. And then what do you think I can do here? I'm having a power rule. Take the power, multiply it to the what? The log. So this is simple as saying 3 log 5 base 10 all over what? Log 5 base 10. And then what can I do? Log 5 base 10 is common to both the numerator and denominator, so they cancel out. So this is equal to what? 3. Which, if I use the normal approach to solve, I'll still get 3 in the end. Thank you. Thank you so much, guys. So this is it for the 6th law, which is the change of base. There are more to that, but when we come back next week, Monday, 4 p.m. West African time, remember, my life, I go live on Mondays, Wednesday, and Friday. And my mission here is quite simple, trying to make being smart the new cool. And transitioning you beyond knowledge to gain understanding. That's what I basically do here. So Mondays, Wednesdays, and Fridays, 4 p.m. West African time, that is when I go live. So make sure that you are there. So let me now talk about the last law, and then we'll call it a day. I want to clean here. I think this should be enough. The 7th law, law 7. What does the law 7 says? Law 7 talks about indicial logarithmic power. Indicial, that is indices, logarithmic, indicial logarithmic, equation, not power, equation. Now, this has to do with the concept of equation. And one thing that I usually say, I like saying it anytime I'm talking about equation. There are basically 2 things that tells you about what an equation is. Now, for any equation, there must be a variable. There must be something that does not add up. Let me put it like that. Something that you're looking for. An unknown. Yes, that's what makes up an equation. And secondly, there must be an equality sign. So that you now have to find a variable, so that once you found the variable, it now completes the what? The given equation. So in that case, if you have something of this sort, for this indicial logarithmic equation, if you have log m base x is equal to log n base x, where m and n, one of them might be the one or the expression, the side that bears the unknown variable. But one thing you can see here is clearly, when you look at this, let me clean here so that we'll be able to solve it together. When you look at these, you see that their bases are the same. And there's a law in indices that commemorates to this. If I have that 3 raised to the power of y is equals to 3 raised to the power of 2. Indices, when we solve a quadratic equation or a linear equation that involves indices, and we'll get to a point where we're having the base and the power. What we simply say is, since the bases are the same, it simply means that their powers must be same. So we drop the base and we now imply that our y, which is the power, is equals to 2 to be able to satisfy the given expression. The same thing also happens in logarithm. Yes, it happens in logarithm. How does it happen? If you look at this left-hand side expression, look at this right-hand side expression, one thing you see that is common is that they have the same base. So if they have the same base, it simply means that the logs are the same. So it simply means that what? Your m implies that your m is equal to what? N. So let's say that we have something like, example, log log 5, log base 5, and then we'll have, let's say, x minus 2 is equals to log 1 base 5. Yes, let's say we had something like this. It's just like a simple equation to tally everything that we've learned so far. Now, what do we simply do? Based on the initial logarithmic equation, they are having the same what? The same log. So because they're having the same log, that means they are what? Sorry, they're having the same base. My bad. They're having the same base, which is what? Base 5. And because they're having the same base, it simply means that their logs must be the same. So it just implies that our x minus 2 is equals to 1. And then we what? Add 2, positive 2 to both sides, becomes x minus 2 plus 2 equals to 1 plus 2. Negative 2 cancels positive 2. Your x will now be equals to what? 3. So 3 is the value that will satisfy this given equation. So this is the initial logarithmic equation. So this is it, guys. I hope you had fun. I really had fun. Thank you so much. I want to give a shout out to those that joined the live. I want to call their name. Kylo, thank you so much for joining the live. Avnish, thank you so much. George, thank you. Watson, thank you. Aspirant, thank you so much. YYY, thank you so much. Thriving Scoop, thank you so much. I really appreciate your presence. Thank you so much for joining today's live. I'll be live again on Monday by 4 p.m. West African time. Thank you, and I hope that you become 1% smarter than you were before you join this live, and that you've transitioned beyond knowledge to gain understanding. Then before I go, I just want to write out my social media handle. You can find me on TikTok with the username at Uncle Sam 160, and then you can find me on Facebook and Instagram with the username Uncle Sam Online Tutorial. So my job is basically simple. I love exploring concepts, and if you don't know already, I am a recent graduate. I graduated from the university last year, and I've always had this passion. I love exploring concepts and breaking down complex concepts in such a way that is relatable. I like bringing complex concepts to reality so that it's easy to assimilate and make it not for you not to fear this concept. That is what I basically do, and I love exploring it with respect to math and other science related courses, but focusing on what? Math for now. So join me. You can reach out to me on TikTok or on Meta apps, Facebook and Instagram with this word username. Just search for me. You see some of the posts that I've made and what you can interact with it. Thank you so much for joining today's live. I really appreciate you guys. Thank you. Thank you. Thank you for your support. Thank you. See you guys on Monday.